Hi, I'm Mr. V, and this is Illustrative Mathematics, Unit 4, Right Triangle Trigonometry. This is Lesson 4, which is Ratios in Right Triangles. Our objective, by the end of the lesson, you should be able to say, I can build a table of ratios of side lengths of right triangles. Now, up to this point, as a brief review, what we talked about in this unit, first of all, was this idea of the American with Disabilities Act. They said that if you have a right triangle and one of the angles is 4.8 degrees, this will be a ratio of 1 to 12. And that's true for any right triangle with a 4.8 degrees. The ratio is going to be 1 to 12. So if I only know one of the sides and I know that angle, of course it's a right triangle, then I could find the other side by setting up a proportion. And this idea is what we're going to be exploring more of today. On the second day of this unit, we talked about half of a square, and I draw the rest of the square here. And each 45, 45, 90 right triangle is going to be similar. They all have two angles that are the same at least. So that means that all three angles are congruent, and the sides would be proportional. What is that proportion? X is to X and X root 2. I don't know how you remember this. One way to remember it is to say two sides are the same, two angles are the same. So it's root 2. And if you don't remember it like that, you could also do a squared plus b squared is equal to c squared, where you have 1 squared plus 1 squared is equal to c squared. So c squared is equal to 2, or c is equal to the square root of 2. So you can come up to this if you were not given this drawing or you didn't know it. You could still do it relatively short order. The previous lesson, we talked about half of an equilateral triangle. So I draw the whole thing. It's 60, 60, 60. Half of it would be a 30, 60, 90. And all 30, 60, 90 degree triangles are similar because of the angle-angle triangle similarity theorem. And they're of the proportion. If the side length is 2, then there's 2 of these y's. This is going to be 1. It's half of an equilateral. The hypotenuse is double the shorter leg. And then this longer leg is going to be root 3 times. And I don't know if you remember that because this is a 30 degrees and root 3, but you could do the same thing with the Pythagorean theorem. Today we're going to look at right triangles, and we're going to look at specific angles and those ratios that are associated with them. Since all triangles with 10 degrees and 90 degrees are similar, that means that their ratios of their side lengths are also going to be similar. That's the big idea. So our first activity was to consider the ratio A to C and B to D. Which is greater, or are they equal? And explain in sentences how you know. Both of these triangles have two angles. By the angle-angle triangle similarity theorem, these two triangles we can prove that they're similar. And the other shortcuts that we use are side-angle-side triangle similarity and side-side-side triangle similarity. We can't use either of those because we don't know any of the sides. We know A and B, C and D. We don't know what the values are. For them to be similar, notice that the triangles are similar. The symbol for similar is a tilde. The angles are not similar. Don't tell me that the angles are similar. The angles are congruent. And the symbol for congruency is a tilde over an equal sign. That's what that means. The sides aren't congruent. If triangles are similar, the angles are congruent, the sides have to be proportional. That is, you can write an equation of two ratios. And if we went from the small triangle to the large, you could say A is to B as C is to D. But that's not what we were asked to show. We were asked to show if A is to C as B is to D. So the ratio of this opposite side from the 20 degrees and the hypotenuse, is it the same as the opposite side and the hypotenuse? If I cross multiply on both of these, I get A times D is equal to B times C. Here we get A times D is equal to B times C. You might recall there are several different ways that you can write the same proportion. I could compare the small to the large to the small, the short leg to the hypotenuse, or the hypotenuse to the short leg, something like that. But these are different ways of doing it. This is correct. This is true. This means that for any 20, 90-degree triangle, a triangle with a 20 and 90-degree measures, that these sides are going to be proportional. And that's the big idea of what we're trying to do today. So in this activity, I put students in groups. And so, for example, here, I'll open up this thing. In the groups, the students were to type in their names. I'm going to go down to one where they didn't do that. Type in their names and on the first angle. And then they're supposed to select this angle and record a measurement for the adjacent leg, the opposite leg, and the hypotenuse, and then do a calculation. Now, what are they doing this with? There is a Geogebra app that I've given you, and you can open it. You have 10 degrees. I can change the angle. Notice this is the angle. This would be the opposite leg. This would be the adjacent leg. This side is adjacent, but it's not a leg. It's a hypotenuse. So this is the hypotenuse. So if I were doing this for, how many degrees were we doing this for? If I were doing this for 40 degrees, I could record the numbers. Adjacent 9.61. Where is it? 9.61. I would record for the opposite leg 8.06. And for the hypotenuse, I would record 12.54. And I could use my Desmos calculator to actually do these calculations. And I want to point out to you what happened when one of the groups did this. So here we have this one group. They did 10 degrees. And they come up with the same ratio each time. Now, some of them took it out to 3 decimals, some of them didn't. And so they get a little bit different answer, but they're very, very close. Very, very close. When we look at this table on page 8, you can see somebody else has done this, and they've done it professionally. They've taken it to 3 decimal places for 10 degrees, 20 degrees, 30 degrees. Used to be, we would have to look this up in books. We didn't have calculators that could do this for us. We're going to show you how to do this with a calculator soon. But notice, for 20 degrees and 70 degrees, this is 0.940, 0.342. For 70, it's 0.342, 0.940. These are the same numbers. This number right here is the same as this one. And you also have the 0.342 is the same as 0.342 here. Why is that? Well, the rest of this discussion talks about that. And there, for instance, here's 55 and 35 degrees. Now, let me just point out to you one thing on my smart board here. If I have a triangle, it's a right triangle, and this is my reference angle. I don't know how many degrees it is. This would be A, this would be B, and this would be C. If this is a 90-degree right triangle, from this angle, this side, and I'll mark it in purple, this angle, this is the opposite. This is the adjacent, and this is the hypotenuse. If I were taking it from this other angle up here, this is the opposite. This is the adjacent leg, and this is still the hypotenuse. It's adjacent, but it's the hypotenuse. Now, if I'm looking at the ratio of the opposite to the hypotenuse, or the adjacent to the hypotenuse, or the opposite to the adjacent. For the purple, opposite to the hypotenuse is going to be A over C. The adjacent to the hypotenuse is B over C, and the opposite to the adjacent is A over B. For the red one, for this angle, it's going to be the complement. Notice these two have to add up to 90 because this is 90. These have to add up to 90. 99 is 180. For this red one, the opposite would be B over C. Hey, that's the same as that. The adjacent would be A over C. Oh, that's the same as this one. And this one would be B over A, which is this guy flipped. Does this make sense to you? Why in the table we have values here that are the same? This one is the same as this one. And also its complement, 70 to 20, the complement is the 20, is this one. Why these are the same? If I take 0.364 and I flip it, I do 1 over that, guess what you're going to get? You get this number. I wonder if that works for 30 and 60. 30 and 60. Or for 40 and 50. Do you see how that works? That's an important thing. So here, the adjacent over the hypotenuse for 55 is the same as the opposite of the hypotenuse for 35. So this would be 0.819. And this one would be 0.574. And the opposite, this would be this flipped. Now, there is a summary page here. You should read the summary page. And you should also try to do this last piece. And good luck and success.